Swayam Prabha. Digital India. Educated India.
Okay, so let's start our discussions. So in the last class we started discussing about convergence of sum of random variables, right. So we said Sn is sum of n random variables, and then we were interested in the case where Sn by n converges in to what value. So we noticed that so if I have a sequence of random variables which are IID, then this value of Sn by n converges to expected value of the random variables, which is expectation of x1. So notice that here what we are saying is the limiting random variable is a constant, and what is that constant? That constant is the mean value of the random variables. So this we called as weak law of large numbers, and we could also show that this is indeed converges also in almost sure sense, but we proved it only under the special case that the fourth moment is finite, and this version we called a strong law of large numbers. So these limiting distributions are very important in applications. So can somebody think of why it is so? So why these results are, I am saying they are very useful. Can you think of an example why this should be useful? To predict the future, what future? But what distribution you are talking about? I am saying it is an IID sequence, right? Every time it will have the same distribution. What to predict there? What we are saying is, what is Sn by n? This is Sn is the sum of the random variables and n. So like he gave an example of fertility rate, right? Let's say number of children per woman. We have it for many women, and we want to calculate what is the average number of children per woman. What you can do? You can just take many samples, talk to many women, and take a survey and then average. Then if you have taken sufficiently many samples, maybe this is going to converge to that value. And another simple case could be, let's say the voting pattern, right? So everybody has a preference for one party of the other, right? Let's call party A and party B. And now you want to see that what is the with which probability each guy is going to prefer. Let's say all of them has a same kind of preference for, like if I have preference for party A with probability P and preference for party B with probability -1 minus P. Let's say that if it is same across all the people, how I am going to calculate that value P? I will just ask everybody, okay, tell me what is your preference. You prefer party A or party B, and then just I will take large enough sample and then just do the average, then I am going to get this value. So you might have seen, right, like all this after elections many people will just say, okay, this guy is going to get this many seats and this many and they are going to say this is going to happen with certain probability. How they will do? Maybe they will just mostly some variant of this results they are going to apply. And usually when they say this, they are going to say what is the sample size they use to make this. Like they say, well, that okay, we talk to 100 people, and based on this our survey says that this party is going to win this with this probability. So and most of the times these surveys are believable if their sample size is large, that they have got this input from more people. If their survey is like, okay, if they have just got and talked to 100 people and from that they are concluding, we may not take it seriously. But if they have talked to maybe like 10,000, 1 lakh people, maybe that is more reliable, because our result says that this average converges to this, and this convergence is more accurate if my n is large. Okay, and similarly, like as simple as if you want to decide what is the success rate of a coin, what is the probability that when I throw up a coin it comes with head, how you are going to find that? So let's say I will give you a coin and it has some bias for coming up head, and you want to compute this head, what is this probability, how you are going to do that? You just keep throwing it and see that how many times head comes, map that head to let's say 1 and map tails to 0, just count how many times you get 1 and then divide it by n, then this is telling that should go close to, as you take more and more samples, that should be go to that value p. Okay, so whenever we have such things to be done, whenever we have kind of parameter estimations, you are going to do this. So suppose let's say all my random variables are exponentially distributed random variables, x1, x2, this sequence is IID, but each random variable is exponentially distributed with parameter lambda. If I take many samples of them, let's say I do experiments, let's say 10,000 times, get the samples of them and then do the average, what will this value be? What is that average will be? Let's say I have an experiment which has a distribution which is exponential. Every time I am going to repeat it many times, each time I am going to repeat it independent of the previous one. Whatever the sample I got first time, let me call that as x1. Whatever the sample I got it second time, let's call it x2, like that. Like this I have 10,000 samples. If I just all add them 10,000 samples and divide it by 10,000, approximately what is the value that you expect? 1 by lambda. Okay, so in this case, suppose if you a priori know that my distributions are exponential but you don't know what is the rate, then what you can just do is do this experiment many times and then take the average, you already got close value of lambda, right. So for example, all this you might have studied in class 12, right, like life of atoms, they will be like kind of exponentially distributed but you don't know the rate at which they are going to decay. Then maybe you collect many samples and doing this you can estimate their rate, the lambda rate. Okay. Today we are going to see one more important results of this convergence of sum of random variables called central limit theorem. Okay, first let me write this result and then we will discuss. Yeah. So what it says is, let us say the sequence of random variable that are IID, and they have this mean and variance sigma square. If I look at their sum like this and then look at their normalized sum. So I am going to call this normalized sum because what is the mean of Sn? N mu. So I am basically subtracting mean already from them, in a way it is centered because each of them are now, it is a 0 mean random variable Sn minus N mu, and then I am normalizing it by square root n. So this is centered and normalized random variable here, and we say that this goes to whatever your sequence is, whatever distribution it has. If it is IID, then it converges in distribution to normal distribution with variance sigma square. Okay. So what does this result say is, now see earlier when I did it in Sn by n, just took the average, it always converged to a fixed constant, but now here the limit is not a fixed constant, it is a distribution which is Gaussian with parameter 0 and sigma square. So let us try to understand why this result is true. So to this prove result, the characteristic function comes to our help, and we just use it here. Let us say, so again I am going to prove this result assuming mu equals to 0. If mu is not equals to 0, you can straightforwardly still conclude this by saying that, so if mu's are 0, this is Sn by n, right. So if mu's are not 0, I could as well write the numerator as xi minus mu I 1 to n, right. So I have just replaced Sn minus n mu by xi minus mu. So this is by definition. Now each of this random variable xi minus mu is, I can treat this as a new random variable, right, xi minus mu. What is the mean of this random variable? 0. So then what I am basically adding is n random variable where each one of them has 0 mean and still their distributions are same. So because of that I can as well assume that the mu's are all 0 and proceed to prove this theorem. Now, so because of that I just need to worry about Sn by mu n, and let us try to find out what is the characteristic function of Sn by n at a point u. So this is a characteristic function of at u, right. So this is Sn by n is, sorry, square root n. And this is a characteristic function of Sn by square root n. Now if you just expand this guy, what you are going to get, so Sn is sum of n random variable where each of them is independent, right. So I am going to get it as product of j xi by square root n of u, okay, and this I from 1 to n. And then what I am basically doing now next is, so now I am going to treat it as characteristic function of xi computed at value u by square root n. right? That is my argument here. So I can write it as I1 to n expectation of j xi and u by square root n, so which is nothing but right. And now because these are all identically distributed, I could write this as well as phi of x1 u by square root of n to the power n. So notice that if they have identical distribution, their characteristic functions should be necessarily the same, right? So that is why we have used this property. All of them should have the same character distribution of that of x1. Okay, now let's try to understand how this guy behaves. So now I am going to use this characterization. So how many of you know Taylor's expansion of a function? So let's say I have a function f of x and I want to do a Taylor expansion of this function around a point f of x, around x naught. Okay, so then I can write it as so in general I can write it as and what is this? This to the power and what is the n indexing happens here? 1 to infinity. But there is an alternate characterization of this Taylor function which says that I could do this as, instead of taking the infinite sequence, I will look at the truncated version of this. What does they say? Then the nth one is going to be so what should be here? It should be I here, right? What is this yn? For some yn belongs to x and x naught. So this is the truncated version of my Taylor series. Okay. So as you see this so you understand what I mean by this superscript I here? This is the ith derivative of this function f. Okay. Now this Taylor function involves the first derivatives, second derivative and higher order derivatives, right? But we will be interested only first and second derivative because I have only first order and second order statistics here. And when I have first order and second order statistics, my moment generating function, I need to only care about first derivative and the second derivative, right? So to write this, let's see what is the value of this function at 0, phi of x1 at 0 when the argument is 0. Whatever the argument is, for any random variable x1, this guy is going to be what? 1. Okay, and what will be the first derivative of this at 0? So what is, I am looking at the first derivative of the characteristic function x1 at the point 0. What is this? So if you differentiate the characteristic function and take the argument 0, what you are going to get? You get 0. So how do you are going to get the compute the mean of a random variable from the characteristic function? I can't hear you. Expectation of? Yeah, I mean I am asking how you are going to derive the mean of a random variable from if you know its characteristic function. You take the first derivative and 0, right? So what exactly I am doing? I took the first derivative and put 0, and that I have assumed to be 0. That should be mu, right? And that I have assumed to be 0 here. And what is, if I take the second derivative and put 0, what I am going to get? Expectation of x1 square, but in this case our mean is 0, so it is variance, but with what sign? It is going to be negative, with a negative sign, right? Just check it. When you second derivative and because of this complex term involved there, you are going to get it as sig minus sigma square. Okay. So now for this characteristic function I know what is the mean value. I mean I have been able to express this, the mean value, in terms of the first derivative and the second derivative of the characteristic function, and I know these things. So let us try to do the Taylor expansion of this only for n equals to 2. Okay. Now, and I am going to do the Taylor expansion of this function around origin, around 0. Okay. So then what will be the Taylor expansion of this? So it is going to be phi of x1 of 0 plus u of minus 1 times, I am just writing expanding for you, but I could have as well skipped this. And here it is going to be not 0, but a value y2 here, which is going to be dependent on where that value of y2 will lie. Zero and u by n. Is this correct? So when I wrote this Taylor series expansion, I kind of expanded it assuming that my function f is real here, but here my phi function could be always real, or it could be complex as well. It could be complex as well, right? So when I have a complex function, all I need to do is this guy is here, is wherever I have this phi I x naught, right? I have to make it as real part of f of I x naught plus j times imaginary part of x naught, when my function f is a complex function, right? So so this guy here, I have to replace it like this, okay, because my function phi is complex. Okay, now let us look at this. This phi x bar, so for the phi of x1, its derivative at 0 is always, it is going to be 0, either it is real or both its real and imaginary parts are going to be 0. So because of that, this guy is going to get 0. Now what remains is this part. So what we have is phi of x1 of u of root n is going to be, again phi of x0 is 1 plus, this is going to be u square by n and 2 there, in the another 2 there, and this one I have to write it as real part of phi of x double prime 0 plus j of imaginary part of phi of x double prime 0. So you see this, when I write this phi of x double prime, its value is minus sigma square. So it has only real part, right? There is no imaginary part in this, right? So because of that I will ignore this part. Okay. What is this going to be? 1 plus u square 2n, and what is this part? This is simply going to be minus sigma square. Okay, I have just substituted the value for this. So what I could get is only this part, but what I am interested in is this quantity raised to the power n. So that is what my phi of Sn by n, right? So now let us go back to that. Phi of Sn by n at u is this whole quantity right. This guy, the real part of this is what? Oh right, it should be for y2, right. So yeah, right. So just let me correct this. What is this guy is going to be? This is going to be yn here, which is going to be 0. Yeah, so I want this to be exactly this, right. Okay, this is fine, right. So and where is this y2 is going to be? U upon divided by n, right, because that is what our that is what we said here, y2 belonging to 0 to u by n, and this is going to be still the real part of phi of x double prime y2. Okay, fine. Now and there is a power n here. So now can you look into this sequence and try to see, you know, are you familiar with this sequence? As n goes to infinity, what this sequence converges to? E raised to this guy, right, but this itself is changing. This is as n, as if you let n go to infinity, right, this itself is changing, and what this y2 goes to 0, and what is the value of this phi of double prime at 0 is minus sigma square, right. And then what is the, can you then what, as this n goes to infinity, where this limit will go? E raised to it is going to u square So you people understand why I got minus sigma square here? Okay, now treat, so yesterday we have discussed that if I have a sequence like this, it goes to e to the power z where Zn converges to Z. If I have a sequence like that where Zn converges to Z, then this sequence converges to e to the power Z. Now look at this. Look at this part, think it as Zn. U square by 2 remains like that. As n goes to infinity, this guy goes to phi x prime double prime at 0, right? And that at that value, what is its value? That value is exactly minus sigma square, and that is why we get u square by 2 is minus sigma square. Now this characteristic function has converged to this characteristic function, this function, and what is this function? What is this? This is a characteristic function of a standard normal distribution, right? That means this has 0 mean and variance sigma square. So okay, this is converging to a distribution which has mean 0 and variance sigma square. So that is why we are saying that my Sn. So if that is the case, we know that so one more terminology. So in general we are going to call, if it is variance is 0 and mean is 1, then we call it as standard normal. So in this case it is just going to mean 0 and variance sigma square. So is it clear? Now so we will come to see, like, okay fine, what is this? Why this central limit theorem is important? So in a way it says that if you have aggregated large samples, okay, and if you center them and normalize by square root n, that aggregation you can treat it to be like Gaussian distributed if your n is sufficiently large, right? So whatever be the xi distributions, I do not care, xi all that could be exponentially distributed or all of them could be uniform distributed, whatever they are, then if I am going to look at their aggregation, normalized aggregation, then if I take sufficiently many samples to aggregate, they will behave as if they are normal distributed. Okay, so in a way I kind of already know how this, with sufficiently many samples, how that distribution going to behave like. Okay, fine. One last thing I want to cover on this topic is Jensen's inequality and the Chernoff bounds. Let us quickly discuss the Jensen's inequality. So how many of you know Jensen's inequality? What is Jensen's inequality? Expectation of fx what is this f? Convex function. What is a convex function then? You know what is a convex function? Yeah, define it. So let us take any lambda between 0 1 and let us take two values. So if I take, so I am defining a convex function now. So if I am going to take lambda x plus 1 minus lambda y, what is this going to be? So if a function satisfies this for all lambda and xy, where xy are in the range of the function, or sorry, domain of the function, then we are going to call this as a convex function. So how does the convex function look like? Okay, let's take 2 points, x here and let's say y here. Okay, so what is this guy here and what is this guy here? So where is lambda x and 1 minus lambda y is going to lie? And where is lambda f of x plus 1 minus lambda f of y is going to lie? So this is a linear combination of the point f of x and f of y, right? So f of x is here, f of y is here, this is going to be the linear combination of them. And what is the function value at this guy? The curve falling? Yeah, so let us say, maybe just to be more careful, let us say this is my lambda x 1 minus lambda y. So what is my function value at this point? This value. And what is my lambda f of x into 1 minus lambda fy? It is going to be on that line. And what is we are saying? Whatever the value of this is, let me make it, this value I am going to get, that is going to be smaller than the linear combination of these 2 points. So if I have a convex function, it is always the case that my function value at the linear combination of those 2 points is going to be smaller than the linear combination of the function itself as those 2 points. Okay, now the question is, if my function f is like this, why it is the case that this is true? So now we understand how the convex function looks like, right? So that is the consequence of this definition. So there are properties one can think of for any convex function for all x. So why this is true actually? So okay, I have a convex function like this. So if you start looking at the slope of this function, so the slope is somewhere here at this point, and if I look at the slope, it will be like this, and at this point slope is going to be 0, at this point the slope is going to be like this, at this point the slope is going to be like this. So what is this slope here? It is negative, and here this is again negative, but this is having a larger negative slope. At this point what is the slope of this, and what is the slope of this guy, and what is the slope of this? More positive, right? So what is happening? The slope itself is increasing. So if the slope is increasing means what? Double derivative is increasing. So that is one property. Another property of this convex function is, at every point I can draw a tangent that touches this function at one point. Okay, so I can draw a linear line at give me any point on this function, I can draw a linear line that acts as a tangent to this function f. Okay, so from this property actually we can right away write this. So let us see why that is true. So take a point x, some point, okay, let me take this x, let me take this y. So this is x and this is my function f of x. At given point y, I can draw a tangent here, that means this line here is a lower bound on my function, right. So what does this mean? I think maybe this much space is enough. So f of x is going to be greater than or equals to L of x, and this is true for all x, right, because this line is, take any point, this line is going to be lie below this function f. Now let us take expectation of these functions, and in particular I would be interested in taking this y to be expectation of x. So expectation of x is going to be somewhere in the middle of my domain, right. So let us take that point to be f y here, and on this point we know that this function and this function both have the same value, right. So what is this L of x? Then it will have some its own slope and it will be like this, right. Now let us take an expectation of this, and this is going to be a plus b and expectation of x, right. Is this true? I just applied expectation to both sides, right. And what is this? At this point this is the line a plus bx, right, this is a plus bx. Now if I compute this function at the point y, which is expectation of x, at that point this value is going to be same as my function f of x. So this is my f of x, right. So on this is simply same as expectation of x. So I am applying this property because this line at the point, so what does this mean? A plus b to expectation of x means this is nothing but this linear function computed at point x, which is nothing but the expectation of x, right. So this is a linear line which is computed at different point a plus bx, but now if I am saying this is a plus b expectation of x, that means this function being computed at expectation of x, but expectation at this point this a plus bf is nothing but f of expectation of x. So that is why expectation of x is going to be greater than or equal to f of expectation of x. So this is exactly is what we said as Jensen's equality. Yeah, L is the tangent. At the point I have chosen this tangent to be at a particular point, which is the expectation of x here. Okay, I know, give me any point on this curve, the convexity properties tells that at this point I should be able to draw a tangent. What I did is I chose a point y, which is the expectation of x, right, and on that point I have a linear function like this, and I know that this linear function always lower bounds my function f of x. So that is the first property I used here, and then just made sure that this f and this L function, they have the same value at expectation of x. So that is why the Jensen inequality holds. Okay, so because of this you can derive some of the properties very quickly. For example, I want to find the relation between expectation of x square and expectation of x whole square, which is bigger. Expectation of x square is greater than this. Why? Can you use Jensen equality? Yeah. So what function you are going to use here? X square, right? So I can think of this as f of x here, where f of x is x square. So if I have to do this, then I know that this is nothing but expectation of x and f is nothing but square function, right? So that is there, and as you said, that we already know that is true because variance is a non-negative quantity and variance is the difference of expectation of x square minus expectation of x whole square. So like this comes handy to prove, this Jensen equality comes handy to prove many inequalities of this part. Some of them are already there in your exercise or in your assignment, try to solve them.